Oh, hello, everyone. This is John Avina from Abraxas. I'm here with Doug Poffinbarger. The reason Doug's here, or I had Doug come on, is because this is something different. It was, in a way, shocking to me because it was something I've never imagined before. Thermal energy storage to me always meant huge, huge tanks, or you can have these thermal energy storage, some people are putting stuff in the walls or above their ceiling tiles, but I don't want to talk about that. I don't like that so much, but the huge tanks, and it was always a huge investment. You needed a lot of real estate and a lot of money to get thermal energy storage going. This is different. It's different. It's Lego blocks that you can put in your mechanical room or on your roof or wherever your chillers are, or or your air handlers. And so I found that really fascinating. So that's why he's here. And Doug, why don't you start by just telling a little bit about yourself, and then go right into it.
Well, thanks, John. I'm a recovering engineer, so I've been practicing energy efficiency and energy management for my entire career. And so I started off in nuclear power and worked my way through energy services contracting for a couple of Fortune 50s. Worked for big energy companies on the supply side, so both sides of the meter, so energy efficiency, renewable, green buildings. Very active with the Association of Energy Engineers for a number of years. I was fortunate to be a past president of AWE SoCal chapter during the energy crisis, which was really cool. That was really fun, very busy, a lot of cool activity that we got to participate in at that time. So if that's okay, I'll get started. And John, I just want to make sure you can still hear me and see me okay?
Oh yeah, everything's good.
All right. Good. So a while ago, 2 years now, I joined this crazy startup company that developed a really interesting technology and really had a different approach towards energy storage that is starting to become mainstream, and it's actually resulted in kind of a resurgence of ice storage or thermal energy storage for buildings. So today my goal is to share with you kind of the why energy storage, when, what, how, and where. That's right, that's what we should kind of talk about in presentation. So one of the things that we're all facing with, or facing today, is heat, especially if you're in the Midwest or eastern part of the US right now. We got this thing called a heat dome. It's the first time I've ever heard that word, and it's just bloody hot. Summers are getting hotter. Somehow, I won't dive into what could be a sticky subject, but with climate change, we are setting records every single year. And what's happening is we've already got a lot of air conditioning on buildings. Of course, you have to exhaust that heat, and so that's tripling. So since the 90s, we've tripled air conditioning installations. And by 2050, we're set to triple again. So it's pretty massive, massive growth in air conditioning. Meanwhile, we're trying to decarbonize our entire grid, and in fact, the planet is seeking to do this. Different countries are at different stages. But we're adding a lot of electric vehicles, and so those are being shipped around the globe. And Tesla's not the only maker, and there's a lot of growth in that, and a lot of battery installations. Prior to that, and continuing to boom, is solar power. The challenge with that is solar and wind are intermittent. Solar only works when it's shining outside. The wind works when the wind blows. And so we've got this kind of gap in energy supply on the grid. Now, why is that important for us buildings? Because we're dependent on that supply. When I started my career, nuclear power plants were 20% of the US grid. Today, there's only about half of those that are still powered up. And the rest are already 42 years old. So now, you add on millions of EVs, you add on millions of heat pumps, new people on the planet, new growth, and of course, all this stuff keeps the economy going. Really, at the stage of Houston, we've got a serious problem. So in order to fill this projected gap of capacity of power, and remember that's 24 hours of capacity, not just 12 or 10 or 8. So we need the equivalent of about 80,000 buildings to become their own virtual power plants. Just think about the raw numbers. It's really, really hard to build out this kind of capacity. And there's no way we're going to be adding coal plants or fossil plants anytime soon in the United States. And the rest of the world is working hard to shut those down. And, politics aside, I know there's different things happen, but it's still a gap. And so what's happened is now you have kind of what we'll classify as good and bad kilowatt hours. So carbon kilowatt hours at night to offset what's being produced during the day, which is generally clean kilowatt hours. That doesn't mean, so we're in this big transition phase. In California, we're ahead of the curve in terms of that stage, which is clumsy, it's difficult. It's a challenge. The folks at CalISO that manage the grid, it's basically a crisis for them every day, because it used to be just turn on the switch and let it run. And now everything goes on and off and you got interactivity, and our grid's not really well built for that. So it's a big challenge for the grid operators. And again, they're kind of relying on us and the buildings to pick up the slack. So as an energy practitioner, that means that we're tasked with a change in how we do our business, how we practice energy management in buildings, energy efficiency, renewables, et cetera. So what I want to point out is that there's a big gap in the margins of energy. So arbitrage, you can think of it that way, is buy low, sell high. So that's kind of how the grid works, but that creates an opportunity for us in the buildings to do the same if we manage them well, i.e. microgrids, virtual power plants. Now, the challenge is there's a lot of buildings in the United States. 250,000 of them have chillers. The big kind of the elephant, the energy hog in the buildings is the cooling loads. So half, on average, 30 to 70%, half the load in a building is air conditioning. But yet, from a storage standpoint, meaning virtual power plants, microgrids, et cetera, there's only 1% are batteries. At the end, you guys feel free to chime in, but I think you can probably guess what some of the challenges are with batteries. I call it the elephant in the room. So you've got environmental issues, you've got, where do we source the rare earth minerals, the chemicals that go into these. There's other fire risks. So there's a number of risks that we have to manage with battery rollouts. And so what that's caused is there's kind of creates a new opportunity in the building space, what I call Wenergy. So how do we manage energy supply and energy demand during the day? It's not about just reducing kilowatt hours. It's what we call Wenergy. So it's a little blurry on this graph. I apologize for that, but this came out of Rocky Mountain Institute. I thought it was a nice chart to post up. Historically as practitioners, we're looking at maybe at a commercial building, and on the left side, looking at demands, and then if we're doing energy efficiency, we're driving the total energy use down. Now you add on solar, PVs, et cetera, then on the third one, you get what we call the duck curve. And that's what we see in California. So you got a big drop in the day, and then it ramps back up really fast, which is what makes it difficult. So by marrying renewables with storage, it's clear that we can much better manage the load. So a nice flat load is pretty easy to manage. So it's a lot easier for everybody, and it's a lot more cost effective and capital effective. So what I want to share is a couple, before I get to the tech, but I want to share kind of a little bit about looking at energy on a daily basis and demand and power on a daily basis. If you look at, let's say, a hospital or casino or data centers, those are pretty flat loads already. although they're very heavily air-conditioned loads. And something to keep in mind here is that the utilities have morphed how they do their billing over the years. John and I have been at this for a long time. We've looked at a lot of utility bills. Today, many of them have shifted towards a demand charge and then a commodity or the energy charge. And in California, it's about 50-50. Half the charge is demand, and then the other half of it's energy. When I was a kid starting at this, it was almost nothing for demand, and energy was the entire bill. So that kind of underpins how important daily demand and demand management really is. And so it's kind of the carrot or the stick, depending on your side of the meter. So if you look at a kind of a common buildings, and what I'm showing here is kind of a load profile or load shapes. And then if you look at the red or the pink areas on these graphs, the filled in bars, that's kind of examining or illustrating the cost of energy during, say, 4 to 9 p.m. If you're a homeowner like me in California, as soon as the time of use rates shifted to 4 to 9 p.m. when it's the crisis on the grid, I run around the house turning off every light. I kind of did that already, but now from 4 to 9 p.m., it's a scolding or an argument if anybody turns anything on at 4 o'clock, if you don't have batteries or some sort of storage in the house. So it's the same with commercial buildings. You could be in the thousands, tens of thousands, hundreds of thousands of dollars. So really important to pay attention to that. So I'm sorry for spending a lot of time on it, but I want to make sure we're grounded in our discussion. So that transitions us to kind of how economics work. We can't have our blinders on and just look at kilowatt hours. We've got to look at costs and savings and ROI, and what are the drivers today in energy efficiency and demand management and distributed generation. So historically, it's always been reducing costs, but a lot in the last few years has shifted to the right side of this table as what can we do about cutting carbon? That's kind of the big discussion these days. Sustainability a few years ago was all about green sustainability. That's morphed into being more carbon specific, or for commercial buildings and real estate investment trusts and big property owners. They didn't used to have an ESG manager before. Now they do, and in some levels, those are C-suite jobs. And so, these are all factors that are coming into the equation and discussion in modern economics today. And so, going back to kind of the what is air conditioning is a big part of the load. So let's attack that, and let's take advantage of that from an energy management standpoint, and see what we can do about it. So I mentioned earlier, batteries are really challenged, but water is really powerful. It's the most abundant commodity we have on the planet. It's maybe getting expensive to pump it around, but it's really abundant. There's lots of it, and it has the highest latent heat in nature, aside from ammonia, and it's really quite energy dense. I think ice is approximately 80 times more energy dense than water. So that's what kind of John opened up with in this. So what Nostromo developed was a way to modularize that, and what's called encapsulated ice. So if we have time at the end, I'll show you a short video, but basically by taking these little Lego blocks, what's more important is what's inside is the capsules. So in this case, we just took sealed capsules and put them inside a container, and inside that container or shell is piped to the chilled water system. And so in this case, it's a glycol water mix because we're freezing what's inside of those capsules, which is just straight water. Nostromo developed a proprietary activation ingredient that allows ice to form much easier than just water on its own. So it's actually organic, so it's fully for a fully organic system, aside from the glycol. Although that can be a propylene glycol, which is pretty organic too. So the ice inside the capsules freezes at around 28 degrees. Historically, with large clunky tanks, you have to get it down to around 22 degrees. So it's less work on the chillers to make ice. And then basically flowing the water through, whether you're on the charge or the discharge time frame. If we're charging it, then simply running cold water in the 26 degree-ish temperature with glycol water mix through that shell. Inside of each of those capsules, which are sealed, are freezing, and then let it sit. And then when it's discharge time, turn on the pumps, flow the water backwards through there, and now you're providing cold water back to the chilled water system or the loop inside the building. And then, and of course, basically, if we pipe it up to pre-cool the chiller system, the existing chiller system in the building, then those chillers, when they have that sense that water coming back, there's a heat exchanger in the middle. I'll show you pictures. Then they're sensing that they're fully satisfied, and they just shut off. If you want to automate it through controls, that's fine too. But the more elegant way is to just put a heat exchanger in the middle and then pre-cool the chillers. But the moral of the story here is that these are just like a modular system, an Icebrik, so with capsules inside that are sealed, no moving parts, just like basically a solid state, clean water-based battery. So simple components, an Icebrik, which is what you see on the top left. Envoy is just the controls for the system, and I'm going to talk a little bit about how we integrate on the grid to the grid in a minute. That's one of the really elegant solutions that Nostromo developed. But from a practical application standpoint, putting the Icebriks just about anywhere, in, on, under, or around the building, or even make something architectural out of them. We have an architect that's designing student housing out of Icebriks. Crazy, but a little bit of insulation, it's pretty cool, but they're basically structural elements. So really the product itself is very safe and sustainable, so 100% recyclable. The shell is aluminum, so extruded aluminum shells. The capsules inside are HDPE plastic. The water is water. By the way, water is renewable for eons. It doesn't degrade. Its capacity to store cold or hot doesn't degrade. And the impact by installing these can be pretty significant, 180 to a couple hundred tons of CO2 per site, depends on where they get their energy from. So very high energy density, long-lasting storage, 25 years plus, and a really low life cycle cost. When we look at the batteries and storage, it's always important, any kind of storage really, is to look at life cycle cost, not just the first cost. It doesn't mean that the first cost is high, but from a present value or an economic metric, you should really look at life cycle costs. So just a reminder for that. I'll talk about the modularity a little bit, kind of the how and the where. So as you can see in these images, I'm gonna blow through some pictures, but you can see they can be stacked up around the parapet walls on a building. A question you may ask is, what do they weigh? So water is not super light. It's about 70 in the Icebrik, fully loaded, about 65 to 70 pounds per square foot. And so most roofs can take one layer of Icebriks because the load is spread. It's not a point load like a tank, so which is part of the elegant solution of this. So they can fit on roofs easily, one layer, two layers with some reinforcement. But they can also be moved around, stacked against a wall. Ground has great capacity. We usually go up to about 10 or so high for stacking on a wall, so sometimes unused space. And then, or maybe kind of creating space. You could create steps or stair or seating area. So there's a lot of applications for these, which is probably really unique. None of us ever thought, I sure didn't before seeing this the first time, thought that you know, a working mechanical system or especially energy storage can become usable space. So that was pretty mind-blowing to me. Here's an example inside of a basement. When we talk about decarbonization, so this is an example of the iconic Beverly Hilton Hotel where the Golden Globes are every year. We designed the system to go up on a roof, and they said, no, we have a basement. We really want you to go in there so we can do show and tell all the time and show our corporate customers that we actually are doing something for decarbonization, and walk them through and show them how advanced we are. So we took a 75-year-old building and actually converted that into an energy management monster. It's terrific, the decarbonization, the demand reduction that happens there every day. I'm going to show you a couple energy management slides on that in a minute. So we've got some cool videos if you want to watch on the website later, Nostromo.energy, that kind of walks you through a explainer video. What I'm taking me 20 minutes to explain and does that in about 6 minutes. So sorry about that. Another kind of key point is by doing something kind of unique, there's a lot of lead points that are available. Up to 20 lead points. So if any of your customers are looking at, or if you're in the consulting business on green certifications, in some cases, just putting in these Icebriks alone have been the green credit and the green benefits have been so significant and enough to do the deal on its own, whether it saves money or not, which they do. Another important point is that like the slide I showed you earlier about electric vehicles, we're adding a lot of vehicles and it's going to keep going. So rather than adding a transformer or building extra capacity, and if any of you have done that, you know that takes a while with utility, and in fact, that's a supply chain issue right now. There's so much growth with transformers that that can be a challenge of its own and an impediment to the building. So this is a way of resolving that. So daily reducing your peak demand frees up capacity inside the building, which enables you to do more with that baseload electrical capacity, i.e. the flat curve we're trying to get to. Now, another key part of this is that storage of old has been something that you just turn on and turn off. I designed my first project 15 or 18 years ago, won an international AWE award. I'm looking at a plaque that you can't see, but that project was put in some tanks and a chill water system. So the first one, I think it was 2013, yeah, so just 11 years ago. And that project didn't have any, it's just automation on the site, but no wholesale or other revenue. So it was just straight off of bill savings. So what Nostromo has done is been able to tie every system together, manage them as a virtual power plant, and do grid dispatch and get revenue for that from the grid, which they share with the customer. So in addition to just bill savings, there's revenue savings. That's not something that's been around, that's ever happened with thermal energy storage till now. So this installation here is what we built in the basement of the Beverly Hilton Hotel. Pretty nice looking room, and fully charges and discharges every single day. That batteries or the Icebriks you see on the left behind all the insulation is and the covering is 1.4 megawatt hours equivalent. Charges and discharges that building every day. On the right side is a charging chiller, and in the back behind the pipes, the vertical pipes, is a heat exchanger. Those are the three main elements aside from the controls that are not on screen. Schematically, it's pretty darn simple. So the Icebriks up on the top, we can add or subtract depending on the capacity that's needed. Usually design that up front. And then, but if the building expands later or needs to contract, you can either abandon the existing ice bricks and just shrink your system size down if needed, or for whatever reason, or to expand it, just add ice bricks. And then on the bottom would be an example of a charging chiller, the heat exchanger, and then everything to the left is the would be the existing chill water system. So daily charge and discharge every day. So without the storage in this example, this is just an example of many, you see the drop off where the green arrows are pointing down. It would look like it's just a solid bell-shaped curve almost every single day with a ramp up in the morning. This is a hotel, if you probably couldn't tell from the curve. So in the morning, everybody starts using energy, they leave for most of the day, and then they come back in the evening. A commercial building might just look like a bell-shaped curve every single day. And so the discharge and the capacity, et cetera, is very flexible, and the amount of charge time or discharge time or charging time can be changed by a mouse click. So it's a very flexible, easy to manage system. And that can change. So if operations in the building change, it's not like we have to do a bunch of algorithms on the BMS code. We just go click, click, click and change schedule and done. And then over time, as the machine learning happens, what we call today AI, then we start predicting how the building is behaving and gets better and better at generating revenue and maximizing savings. So what the DOE has seen in this is the virtual power plant. So if you pay attention to the United States Department of Energy, you'll see a lot of discussion about, and discussion not just talking to the wind, but they're very strategic and targeted discussions with utilities across the United States, with big stakeholders across the United States to get serious about virtual power plants. That early slide I showed about that drop is a big deal. The Inflation Reduction Act is supporting of this. Side note, Nostromo is getting a couple $100 million to deploy the next couple hundred systems, funded by the Department of Energy, and so it's a capital project capital fund to deploy these systems. And so it kind of underpins the value of what a virtual power plant is today. So you hear a lot of that discussion if you haven't already.
Hey, Doug, does that mean that these clients are going to get the systems for free, or they're going to get them for half off, or since the government's paying all that money?
It's project capital, so it's really low interest loan basically to the project. So now there's two forms of offer, since you asked. One is customers can buy them. They can still get, there's more on that, it gets even better. Actually, let me save that to the end because it's really pretty cool what capital is available today. Now on the grid edge technology, this is just a quick graph to show you that there's actual grid integration. In the state of California, Nostromo is already qualified for resource adequacy, which is kind of like demand response, or if you're on the front of the meter side, you would inherently know what that means, because it's basically, I've got capacity available to bid into the grid. Most people think that capacity is generation going onto the grid. It's actually, the grid doesn't care as long as it nets out to that supply meets demand. If you drop demand down, then the supply can drop down. So it's the same, the delta is what resource adequacy really is. And so that, in our case, in the case of behind the meter storage, it's the demand reduction that's controlled and flexible that enables that resource adequacy. So it allows Nostromo to bid into the grid and say, I've got this much capacity available this day and these times, and then get paid for it, and then of course share that with the customer. And then this is just a quick notice to show that I'm not just talking about this. This was actually published. So a lot of benefits, kind of underscoring to the customer that there's financial benefits, there's environmental benefits, operational benefits. So everybody kind of wins that's at the table. And then, of course, the community wins too. So it enables faster growth of renewables, particularly if you can. I'm a big behind the meter fan. If you can distribute those renewables and put it on your building, you control your destiny. It creates local jobs because people got to install this stuff, and then it hardens the resilience and gives us all, energy security. We're not worried about PSPS events. And then I'll talk about the money at the tail end, which is really substantial. Inspirations, I'm going to run through some quick pictures, just some screenshots. This one's on top of a building in the middle of, this is actually in Jerusalem, quite hot every single day. So desert, less than, I think around 3 or 4% thermal loss, which is de minimis, and then recharges every single day. Data center operation, so outdoors next to a hospital, no issue with risk, no HCI or OSHPD issues. Here's next to, John mentioned this in the beginning, in a chiller room, next to a chiller room, just stack them up where you have space. Stairs, this is at a university. This is creating space next to a central plant for distributed district cooling system. Here's on a rooftop. This is actually the model that we did for the Beverly Hilton initially. And then they said, no, let's put it down in the basement just below there. I think I showed this rendering already. And then, this is, we're actually on my boss was in Time Magazine, so it's kind of cool. John, if you're okay routing this afterwards, or we can make it available through you. So there's a lot of cool ways of implementing. And I'll just share before opening it up to Q&A and talking about the money next, is that it's pretty dense. So the system I built, got that international award for, is on the right. We had 3 tanks. And if I was doing it again today, of course, whether I was employed by Nostromo or not, I would still use this solution because I think it's a more elegant, better solution, especially for the space and the real estate. And it takes up less real estate for the same amount of energy density, and it can be hidden. So sometimes you want to show it off, and sometimes you don't. Now, John, you mentioned the cost. So the Inflation Reduction Act had a change to the investment tax credit. The investment tax credits allows, that's not a deduction, it's a credit, which means basically it's like a rebate. So if you have energy storage system, it's a 30% tax credit. If it's USA made, it's a 40% tax credit, so an extra 10% adder. And if it's in a federal economic development zone, there's another 10% adder. So tribal nations or economic zones all get that 50%. So it's a half off credit or rebate essentially for buying one of these systems. So, I mean, half off is half off. It's a pretty nice deal. Now there's incentives and other rebates that are available that can drive the first cost down even further. And then, of course, there's the bill savings and the wholesale revenue savings, which makes the ROI fantastic. And then the DOE money that I mentioned has allowed Nostromo to provide this as a service. So we just basically take that capital, capitalize the cost of the project like low interest loan, and securitize it through the DOE. And then of course, taking the tax credits, and that gives a really immediate payback because the customers don't have to write a check at all to install this system. So the question is, what is this system? And if you remember that schematic that I showed, basically everything in red, including all the labor, is available for the ITC. So that entire system, including the charging chiller, is ITC. Now, if any of your listeners are facility managers, the resilience part is probably pretty important. So if, just like at home or anywhere, the question is, when does your air conditioning go out? Well, when it's hot outside is when it's taxed the most. So if you don't have an extra chiller sitting around, many do, you have an N+1 or an N+2 maybe. And if you don't have that extra capacity in the summer, then then that's when the trouble calls happen and you're bringing in a temporary chiller or sending people home. Having this extra backup charging chiller, and it would be like an N+1, and then the Icebriks would be an N+2. In some cases, maybe you're considering, or you've got an older chiller or a couple older chillers. We have many applications like that. You got a 20 or a 30-year-old chiller. It's at the end of its life, and you need to replace it. So what you would do is go out and spend $500,000 on a new chiller. Instead, maybe you spend that same money and get a chiller and an energy storage system backed up, automated, and grid revenue, because it's all part of that. So this chiller, what I'm saying is, can be operated in support mode to support the plant, or it can be plumbed up such that it's part of the system and it's all available for ITC. Can't buy everything under the sun, but everything that's required for charging of the system is available for the ITC. We wrote that into the tax code. I think that probably ends the discussion, and then at least, my part of the discussion. So John, I'll turn that over to you.
Yeah.
To add to that, and any Q&A, I'm happy to answer.
Yeah, I've actually got a lot of questions. Okay, number one is, you might have actually answered them earlier, and maybe I wasn't paying enough attention, but these modules, it looks like you only have one size. Is that correct? It's just one size fits all, kind of like Legos?
Yeah, each Icebrik, we're, as a newer company, we're going to start adding new stuff over the years and as the need comes up. But an Icebrik, a single Icebrik, we usually put multiples in there, is 14 feet long. And the cross section is 20 inches wide by 10 inches tall.
Yeah, that was my next question. And then how much does it weigh when it's filled with ice?
So each one is 65 to 70, depending on the plumbing connections on the end. So about, conservatively, 70 pounds per square foot.
Yeah.
I think they're each, one alone is about 1,000 pounds.
About 1,000 pounds.
Right.
Okay.
But the key thing is the pounds per square foot, just like you look at solar or something like that.
Oh, right. Yeah, for roofs.
Spread. It's not a point load, which is the big difference between these
Right.
and a tank.
Yep. Okay, so assuming you get a 30% tax credit, just 30, what kind of payback would you get in Los Angeles?
Interesting
More
question.
or less, a range.
So most of California, the payback is about 4 to 6 year simple payback.
Okay.
LADWP is like this kind of anti-storage bubble. They're not that bad, but their demand charges and the way their rates are structured in LA are nothing like the other territories. So keep in mind, we're working on them, and we're making some progress. I think we're starting to have some discussions about potential either grants or incentives. They need this like everybody else needs it. They need storage for their part of the grid, but they are kind of standalone and a little bit longer beast to develop.
Okay, here's another one. What about in Dallas? Have you installed any systems in Dallas?
Currently, no. Nostromo's focused in California.
Okay.
Now, Texas, the state of Texas is on the radar. So we're plotting our next couple states that we'll deploy to in the next couple years.
So if
we are seeing up projects in the state of Texas, but we won't deploy until maybe at best case mid-25, maybe early 26.
Okay, so this audience is international actually. What states in the U.S. can you deploy to this year?
California this year, and then, like I said, we're looking at our other states. Now, let me clarify something.
Okay.
When I say deploy, I mean the energy storage as a service option.
Oh, that. Okay.
Nostromo backs up. We made a promise to the DOE that we were going to focus in California for that capital.
Okay.
Now, if it's a purchase deal,
Yeah,
anywhere you want to ship it, anywhere.
even in the world.
Yeah. Now we'll support the engineering. So we've got engineering support for that. We could
Okay.
do everything turnkey in California, but other states will support firms that want to do the analysis and the modeling and the construction. We'll support that. And then we'll come along behind them and help operate the systems after it's commissioned.
Okay, here's another one. So suppose you do this as a service. When I'm thinking about this in terms of like if I was an M&V person for an ESCO, and every once in a while we run into these projects that are underwater. We're just not making enough savings because who knows why, but we're just not getting the savings. And always we're looking for, are there simple projects that are cheap that we can do that will generate a lot of savings? And it sounds like your service, actually, it's free. so like they ask to pay anything or pay very little to get you to install this. Would the customer get any money out of this though? Would they, or would you reap all the savings, or would the customer, who's, let's say was a hospital, would they actually reduce their bills because you're doing this as a service?
Yeah, so we go to market in two ways. So as a service where we own and operate the system, we share the savings with the customer. So in other words, that customer is getting a benefit. It's not all going to the grid. Grid benefits.
That's killer.
Customer saves money and or makes money. And then on a purchase deal, of course, they get 100% of the value now of the bill savings. And then on the wholesale savings, they want to hire us because we are the grid operator basically for the systems, and then we'll share that savings with them. So either way, the customer wins.
Okay, that's good. That's really good. What's the minimum cost for a system? I know systems can be all different sizes and all of that, but what would be the cheapest system you've sold?
Typical kind of system size these days is a range of 1 million to 3 million bucks.
That's expensive. Okay.
Now we've got smaller ones and we've got some really large ones that are being developed now, and then so it can get much larger than that. The scale is somewhat infinite. There's some properties that are massive in size and district energy systems that are being looked at because it's a whole new way because of the real estate, right? Real estate's expensive, like you pointed out. LA is really expensive, and many other cities are. So this is coming to play in much larger systems and campuses and central plants.
Okay. And essentially this works really well if they've got high demand rates, high peak demand rates, not just demand, but peak demand. That's where it really works, correct?
Yeah, there's two things that we kind of look for. Number one is the demand or energy arbitrage, or both. California has that in spades. And then wholesale revenue. Can we sell to that market? It takes a while to set those up with the PUCs and the independent system operators. Hence, we started in California. We're focused here first. But the behind the meter, the retail savings is focused on the first part is the swing between the peak during the middle of the day and whatever that peak hour is. We don't care what the hours are. What's important is that there's a delta or an arbitrage in there.
Okay. When you use these as seats outside, I saw it, are they cool? So let's say you did this in Dallas or, in somewhere really hot, and you put these outside as seats, your storage, would they be cool to sit in?
Yeah, you can do that. So insulation is amazing.
Okay.
Ideally, we can do whatever the customer wants, but from a standpoint of insulation, you've got a couple things to think of. Number one is it comfortable? First thing, if it's around you. Number two is it maximizing the energy that we're keeping inside of those cells?
Right.
And that's expensive. And then
Right.
number three is condensation, like a glass of water. So we typically don't want a whole bunch of condensation around unless you're designing specifically to have condensation.
And so you probably put them in the shade then. You don't put them in direct sun, right? If possible.
Really, yeah. We can if there's a necessity. That's probably the last in the pecking order of choices. but I
Okay.
showed you a picture of one in the hot baking sun in Israel, which would be like in the middle of Arizona.
Yeah.
And we insulate it well, have a nice sheathing over that, and we measure, I mean, to the T. We measure the energy production, the savings. We've got like 50 data points in every system. And then we even measure the carbon. I should have pointed that out, I just realized. So we're monitoring the carbon on the grid. There's some companies now that are monitoring on an hourly basis what the grid is producing in carbon wise, you know, how much gas or oil or whatever. And then we, of course, monitor exactly how much we discharge on a minutely basis. So we can log all the carbon that's being offset by use of the system every hour, every day for infinite time.
Another question, if you install this, do you have to use your control system or can you just use your own BMS?
Part of what comes with the system is our management system. So that's one of the reasons why we did that is so that we can keep the cost down. It's not a science project every time like most installs are. It just keeps it consistent and similar. Now we can connect up with somebody else's BMS if they want to pull or see some data, or if they want to have some basic control over that. But honestly, and then it's all cloud-based. It's not necessary, but it can be done if the customer really wants that.
Okay. What's the difference between this and the ice storage Model C from CalMac?
Good question. So I think I showed you a picture of the tanks. So their tanks are ice on coil. So a couple differences. One, just on the outside, is the size of the tank, the weight of the tank. It's very limiting. They're less expensive per gallon to make because it's just a bigger tank and you fill it with water. And so good product. It's been around for a long time. The design from operational standpoint is ice on coil. If you think about it, you're forming a big block of ice. And then when you discharge it, you're melting that ice from the coil out. And what happens is you start forming a micro insulation barrier around it. And at the end of the day, you don't end up with good linear control of your ice melt or your freeze. And then if you lose a coil, then you lost your whole tank. If we lose a capsule, you don't even notice it. And the testing that we've done has 99%. Nobody says 100% because of liability stuff, but over 20 years, we have less than 1% degradation.
And yours, though, are blocks. Theirs are cylinders, is that right? And yours are blocks, is that?
Yeah, those are cylinders, and ours are blocks that can be moved around and shoved around.
Yeah, so yours are also more portable and easier to put in different spaces, and theirs are more limited when you're trying to fit them places. And like you said, there's more pounds per square inch if you're putting it on a roof than yours, because yours is spread out.
You don't have to be in one space. We can be spread out, and again, we have the full virtual power plant and the wholesale grid revenue, et cetera.
Okay, here's another one. What's the optimal location for maximizing the thermal efficiency of this portable TES system? Would it be the basement, roof, steps, or sidewall? Yeah.
Thermal efficiency basement where it's cool. You know, the colder you can keep it.
Yeah, that makes sense.
Doesn't always mean that the installation is the best. Meaning, if it's like the Hilton I showed you, which was interesting, we brought in that whole system through a 3-foot corridor. Imagine that. You have to cut everything up to do that with a tank.
Right,
so
absolutely.
Build it and weld it on site. We brought it through a 3-foot door. And now, so really that's kind of get to the site specific deployment. Is it cheaper to drop something in off a crane? Is it easier to just set it outside? That's part of the ROI, is where do we put it and where's the ideal place? Thermally in a basement.
What types of facilities, regions, or states, based on load profiles, are the most suitable candidates in terms of payback? You know,
highest demand charges, where you have some arbitrage between the day and the peak and off peak, and you don't get hammered by off peak charging. Period. California is a no-brainer. Hawaii, Texas, Connecticut, some of those states. And then it brings up a whole new point, which I won't belabor here, but Local Law 97 in the state of New York is punitive. If you have carbon in your buildings, they don't care if you're making it yourself, which would be source one, or if you're buying it from the grid, which is source two. You're getting billed, and it's sending a shockwave through the commercial real estate market in the city of New York. So that's a whole nother kind of can of worms. Some states are leaning towards that, and some states are just holding out big carrots, and some states are between a carrot and a stick to incentivize this.
Do you know anything about Denver and their utility rates? Do they have high demands there?
We did look at it. We're looking at a project in Denver, and I don't recall how high they are. I know they're not like California. Nobody is, but it's moderate. I think that's Excel Energy.
Okay, here's another one. Can you walk through the CO2 reduction you mentioned? There's more to this question, so don't walk through it yet. I had installed 2 TESs back in the early 90s and hadn't seen much, if any, kilowatt hour reduction. Well, yeah, I can see that. So would your CO2 reduction be explained by the power generation at night, that is part load efficiency? If your e-grid plants had a higher percent of PV generation, CO2 less, cut into your CO2 savings. The first TES I put in also helped to offload the generator part of the AC during power outages for one time through a critical research lab. Yeah, that makes sense, because thermal energy storage in general doesn't always save kilowatt hours. It could actually use more, but it can save you a lot of money because you're reducing, you're on peak demand. And so then if it's not saving kilowatt hours, how are you saving CO2? And yeah, that was an interesting question.
Yeah, that's a money question. So storage is money, and that's the primary thing. Now, most of the time, the kilowatt hours are neutral, sometimes an add, and sometimes a savings. Let's say you got an older chiller plant with like maybe it's air cooled, or you got a high kilowatt per ton, poor COP, and then we're charging and getting the diurnal effect at night, et cetera, we can save kilowatt hours too, and of course drive down the demand.
Yeah, sometimes it does. Yep.
In some cases, like let's say a campus or a central plant, maybe they're running at part load at weird hours, and then their COP is terrible during those hours. Adding some storage and just discharging and offloading the chillers completely during poor hours can be a huge savings to them. So it varies, and it kind of is site specific.
Yeah, I buy that. Yeah, they could bring on the less efficient chillers when they have to, when it's super hot.
Yep.
Now you don't have to do that.
Yeah, we're adding a super efficient charging chiller. We run that in support mode. Boom, there's some kilowatt hour savings. And then I think the Wenergy is the really important part here, is when you buy that energy and electricity during the day. The carbon is precisely, I think they got it. So if your normal generation is, we'll use the example of nighttime. So fossil fuel plants kick in at night, heavy carbon. So if we can run the charging chillers, et cetera, with solar energy, then you're reducing the amount of carbon that you're relying on. So it's just a matter of shifting the loads to different times where you have that delta between the carbon production.
It's all interesting. Yeah, it's good. Yeah, right. And in California, some of you folks don't know this, maybe you all do, I don't know, but peak in California, what is it, 4 to 10 or 4 to 9 p.m.?
4 to 9 p.m., 5 hours.
So yeah, when the sun's up from 8 in the morning till 4, you can be charging because it's not peak. I mean, you could be, if that's really what you wanted to do, is reduce your greenhouse gas. That would be one thing. Here's a question. What supply temperature is suggested for charging?
So usually during charging mode, we'll run the chiller in around 26, 27 Fahrenheit to charge the Icebriks. So the glycol water system in our loop is around there. And then, discharge will discharge at, low 30s or 20 or something, depending on the piping. And then pre-cool their chill water loop. If that makes sense.
Okay, here's another one. Can you elaborate on the energy storage as a service option? How does the shared savings look like? How much is the customer able to retain typically?
So short answer is typically about a 10, depending on the application, 10 to 30% reduction in their cooling costs. I can't cover their whole load because we're only covering the cooling system. So if, let's say, just for level setting, if their cooling is half of their entire bill, then they should get anywhere from a 5 to 15, maybe 20% reduction in their total annual utility cost, somewhere around there.
So they get about half. Is that what's going on?
Well,
half.
We cover the cooling costs. So if cooling is half of their total bill, then we'll cover, then we'll share with them. It'll be, if it's energy storage as a service, it'd be about 15 to 30% off of their cooling costs.
Oh,
there's
15,
nothing magical about it. It's really just project economics. You've got a capital expense to build the system, for all the parts and the labor, and then that has to be paid off over a reasonable period of time, typically like around 10 years for our money. And then so some of that has to go towards paying off the capital, and then the rest of it goes towards the savings. So
okay. What's the typical time frame required to scope, design, contract, and implement one of these systems?
It's funny because I don't know about you, John, but for my whole career, most of it, the hardest part was just getting utility bill interval data out of the utilities. And then right now, that's gotten a lot easier. Now the hardest part is getting chiller logs, so we can see the heartbeat of their chill water system, so we can size it right.
Wow.
I'm surprised how hard that still is. And then so that can take anywhere from a day to a month, depending on the customer. But that aside, the rest of the work is a few weeks for scoping, site assessment. Maybe run a month or two, depending on people's schedules and customer schedules and access. And then we get into the final design for the deployment. The design work, the system's designed already. The design work is really how do we apply it to that site? Where do we put everything? Getting permits and stuff. So that can be 3 to 6 months. And then installation can be, the fastest is probably, weeks. The reality is probably, 1 month, 2 months. That Beverly Hilton project I showed you is probably one of the more complex ones that will happen. Old building, customer operating every day, shutdowns for big events, and all the stuff that's going on. That took a couple months to build once we got the clearance. We don't need an agreement, so permitting is fast. It's just like buying an air conditioning unit. However fast that AHJ is the permit speed.
Okay, I'm gonna. Do you have any last words before I show the next few webinars coming up? You did a nice job. It was really interesting. It was good.
Thank you. We're happy to help. Questions, just route them on over. We're Nostromo.energy. 858 Nostromo is the phone number if you want to call the corporate number. And just happy to help. If you got projects to look at, ping us, doug.p@nostromo.energy. And then my just thanks is to you guys and all the fellow practitioners that work so hard and tirelessly to do good work. I just love our field. I love the engineering aspects of it. I love what we all do, and in it with you guys. So just thank you for your time and patience and listening in. Thank you, John, for the